Lab 2, Motion of a Falling Object. In Lab 2, we will explore the dynamics of a falling object. The goal of this lab is to study the behavior of a crumpled piece of paper as it falls from rest and then to analyze its motion using a software called Tracker. We will develop a few different models that will help us understand how the forces of weight and drag influence this motion. Our approach will involve a few various steps, including 1. Observing the paper's fall, 2. Graphing its motion, 3. Creating a model that will include only the effect of the weight force, and then 4. Developing another model that accounts for both weight force and drag force and comparing these two aforementioned models. Now here's a video of the fall of the crumpled piece of paper. Now, using the Tracker program as such, we first determined the approximate size of the crumpled paper ball. The coordinate axes were oriented such that the paper falls in the negative y direction, and as the object moves, its center of mass is marked and recorded. The recorded data points then are plotted as shown in this image. Now here is a graph of the observed motion or actual motion of the paper in good resolution. Now, to better understand this, we'll compare it to a model that only considers the weight force acting on the object. Here are the two graphs for comparison. Now, the first graph shows the observed motion of the paper, whereas the second graph includes both the observed motion and a computer-generated model of how the paper behaves when only the weight force is applied. The code that generates this model is displayed on the right side. Now, in the code, the mass of the crumpled paper was essential to calculate the weight force. Newton's second law, in short, velocity final equals the initial velocity plus the net force divided by mass times the change in time. And this was used to calculate the object's velocity. The net force in this case is equivalent to the weight force, which is calculated as the product of mass and the gravitational constant. Now, we'll introduce a second model that includes drag force. And on the left are two graphs, the first one being the previous model, only the weight force, and the second graph on the right is the model that includes both weight and drag force. Now, in this new model, the weight force remains unchanged, but the drag force is added, and it's calculated negative b velocity squared times the unit vector of velocity. Now, using trial and error, we determined that the proportionality constant is b, as pictured on the screen. And while most of the code remains the same except for the net force, which is now the sum of the weight force and the drag force. Now, the drag force is proportional to the square of the velocity, and the magnitude of the velocity was calculated using Python's mag function. Now let's discuss the results. So in the first model, which only factors in weight force, the crumpled paper's position changes at an increasing rate because acceleration is constant and positive. However, in the second model that includes drag force, the acceleration gradually decreases, eventually reaching 0. Now, as shown in the second model, terminal velocity is reached when the drag force bounces the weight force, causing the velocity to stabilize over time. And the first model does not accurately predict terminal velocity, so that'll be the second model. Because as the acceleration remains constant, the object continues to speed up indefinitely. Now the question, does an initial velocity affect terminal velocity, is a good question. Now, to answer this, we can examine a case where the crumpled paper has an initial velocity of negative 0.5 meters per second. Now, even with this starting velocity, the paper still reaches terminal velocity. However, the displacement at which terminal velocity is achieved differs from when the object starts, at rest. Now, it's important to note that this holds true only when the initial velocity is less than the terminal velocity. If it exceeds the terminal velocity, a different outcome would occur. Now, in conclusion, models that include both weight and drag forces successfully predict terminal velocity, as the forces eventually balance, causing acceleration to cease and velocity to stabilize. On the other hand, models that only consider weight force fail to capture terminal velocity, as the object continues to accelerate without limit. Thank you.